we've already seen all this stuff on Monday, so I will repeat something, then I will also try to explain it maybe a bit differently. So, or maybe you can sleep if you know it's not a problem for me. First I will begin with maybe an observation, or I don't know if I can call it an observation. Or maybe a motivation for defining the augmentation category. If you remember, so I write some names, long names, a lot of names. Kompromski, Sablov, and Walker. So if you remember, on Monday, we saw that if you have a Legendrian in, for example, a P cross R, where P is a Liouville manifold, or you can imagine in one jet space of manifold, or R2n plus 1. If you have an augmentation of the Tchekhanov-Eliashberg DGA over Z2, for example, you can conjugate the differential by DGA morphism. So this was done on Monday to obtain the linearized Legendrian contact homology. So I remember you that phi epsilon on wave chords acts as A plus epsilon A. And this differential restricted to C lambda, the Z2 vector space generated by wave chords, can be decomposed as a sum of di epsilon, where I is greater than 1. And di epsilons, they are from C lambda to the tensor product C lambda I times. And so now we can, d partial epsilon is a differential, so this squared, this is 0, and you can, so this relation can be written or rewritten using the di, and so if you written it with the di, you obtain the relation that for all d greater than 1, you have that the sum of m going from 1 to d, the sum n going to 0 to d minus m, of, well, maybe it's a bit long, I'm sorry, it's a bit long, of the d m epsilon tensor with identity n times. You compose it with d epsilon d minus m minus 1, and this gives you 0. Or this is another way to write this relation with all the di. And now if you dualize the di epsilon, I write it mu I epsilon. So this is a map from C lambda A times to C lambda. And if you dualize this relation, you obtain the A infinity relation. So which is, well, it's the same. Well, it's not exactly the same, but for all d greater than 1, you sum over the same indices. And the relation is mu d minus m minus 1 epsilon identity d minus m minus 1 tensor mu m epsilon tensor identity n equals 0. And this is the infinity relation for all b.
Sorry, in the dualized, are you taking duals of the kind of the Ashford algebra?
Oh yeah, So, Well, I write it the same way by abuse of notation.
Okay.
Yeah. So what we obtain is that the algebra, the Chekhov-Eliasberg algebra with the operation with the mu e epsilon is an infinity algebra. So this is the first step before having an infinity category. So
I think really it's instead of A of lambda, this is C of lambda, right? It's
yeah.
vector space.
It's
the infinity algebra, you start with the vector space and then you have mu operations on it.
Okay,
Or C
I
star,
thought it's the
I don't know.
tensor algebra over C lambda.
No, but not the tensor algebra, right?
Yeah, taking tensor to define infinity structures. It's not the algebra.
Okay.
I think we're all saying the same thing, but
Okay. So this is an infinity algebra, and now the idea is what happens if I don't take just one augmentation but several augmentations, and I will obtain an infinity category. So let's begin with 2 augmentations instead of 1. And we'll have the bilinearized Legendrian contact homology. So if I take epsilon 1, epsilon 2 augmentations of A lambda, what will be the bilinearized Legendrian, the bilinearized differential? So I write the formula and then we can see on the trefoil an example. So this is partial epsilon 1, epsilon 2. So how is it defined on rep chord? So I take a rep chord A. A is a rep chord of lambda. I sum over all the chords B1, Bm, such that, well, there is a degree. The sum of the degree of the Bi is the degree of A minus 1. And I sum over all I between 1 and m. And then I count. So everything, I will do everything with Z2 coefficients. So I count some moduli spaces of Legendrian contact homology. But then I augment by epsilon 1 and epsilon 2, or maybe I put epsilon 0 and epsilon 1. So I augment by epsilon 0 the chords B1 until Bi minus 1, and I augment by epsilon 1 the chord Bi plus 1, Bm. And then I add the chord Bi. So this is a formula for the bilinearized differential. And this is a way to obtain the bilinearized differential from the Chekhov differential, because those are moduli spaces of Legendrian contact homology. We saw it on Monday on the talk of Daniel, I think. He described those moduli spaces. So we can look on the trefoil how we can compute this differential. So Marco told us on Monday how to compute the differential when you take the Lagrangian projection of your knot. So this is the Lagrangian projection of the trefoil with 5 red chords, and you can compute. I think Marco, you explained how to find 1 and B1 and, well, maybe not all the differential, but almost all the differential. So you can compute that the differential is this one. And so now I have this differential and I want an augmentation and I want 2 augmentations at least to compute the bilinearized differential. So how can I find an augmentation? Ongao told us how to find an augmentation from the differential. I use the property that epsilon composed with the differential gives 0. And so when I apply this to my differential, I obtain this relation. I have just one, the 2 lines give the same relation to find an augmentation. And when you resolve this equation, you can find that there are 5 augmentations. I wrote just 2 of them to calculate the bilinearized differential. And now, how we have to do. You have the differential, and you want to have a linear application, and to have linear things, you choose you in each word in the differential you keep one chord and you augment the other chord. So if I calculate for A1 the bilinearized differential, so this is the one, so it disappears in my, when you linearize the constant term disappear. So then I have B1, so I keep B1 and I have no other chord to augment. I keep B3. And then here I have 3 chords, so for example I can keep B1 and augment B2 and B3. And as I am computing bilinearized differential, I can augment by epsilon 1 or epsilon 2, but I decide that when I keep a chord, on the right I augment by epsilon 1, on the left I augment by epsilon 0. So here I keep B1 and I augment by epsilon 2, B2 and B3. So this term. Then I can also keep B2 and augment B1 and B3. So I augment B1 by epsilon. Oh. Okay.
But that's fine.
It's okay. It's okay.
It's okay. Okay, this example is with epsilon 1 and epsilon 2. Okay. So I keep B2 and I augment B1 by epsilon 1 and B3 by epsilon 2. And the last term is I keep the chord B3 and I augment the first 2 chords by epsilon 1. This is the last term here. And as you can see, for those 2 augmentations, epsilon 1 of B3 and epsilon 2 of B3 gives 0. So all those terms disappear. This one disappears because epsilon 1 of B2 is 0. So this one also disappears. And so I have that the differential of A1 is B1 plus B3. This is the bilinearized one. And you can compute the same thing with A2 and you obtain that the bilinearized differential of A2 is B1. So then the differential of the BI's will be again 0. So that's all what I have nothing else to compute. And you can see that, so if I take the homology of this, maybe I didn't say that, so the homology of the complex C lambda, okay, I keep epsilon 0, epsilon 1 here, of this complex is the bilinearized Lagrangian compact homology. And we write it LCH epsilon 0, epsilon 1 of lambda. So we can compute that in this case, the bilinearized Legendarian contact homology is one-dimensional and it's concentrated in degree 0. So why? I have 5 chords, A1 and A2 have non-zero boundary, and B1 is a boundary, and B1 plus B3 is a boundary, so B3 is also a boundary, and I have just B2. So the Legendarian, the bilinearized homology is generated by B2. Yes?
Sorry, just a sanity check. So you have a differential on the free vector space generated by red chord, not on the algebra.
Is there a Leibniz rule?
Oh yeah, oh yeah. Yes.
It works.
So what am I doing? Alright.
You have a Leibniz rule you want, but for linearized contact homology, you're only taking the degree 1 part.
I mean, that was used to show that the infinite algebra satisfies the infinity equation.
Yeah.
But otherwise, if you just want to compute it, then it's satisfied.
So the bilinearized contact homology in this case is a one-dimensional vector space,
Yeah.
not the free algebra generated by the
No.
Okay.
It's a vector space. It's a Z2 vector space. Yes.
Thanks.
Yes. Sorry. Okay. Are there any other questions? Yes.
Is there a particularly good reason why you should use 2 augmentations instead of 1 or 3?
Well, if you use epsilon 1 equals epsilon 2, you recover the linearized Legendarian contact homology.
Oh, the main point is that this way you remember something about non-commutativity of the algebra. On one side you apply something, and then on the other side you apply something else. On the other hand, this type of definition is the same thing as taking 2 copies, and then consider a composition rate of black holes going in one direction.
Yeah, that's what
Yes.
I will say now.
No, but also you can consider more than 2 augmentations. Those are the higher operations in the infinity algebra.
You want to consider more than 2 augmentations?
Category,
you?
sorry.
Oh yeah,
Yes.
you can, but well, you know, when you linearize, what I wrote, you have the linearized differential is a sum. You can decompose it as a sum. So what you can do, well, so the bilinearized Legendarian contact homology corresponds to generalizing the case where I equals 1, and then I can maybe 3-linearize, or I don't know how to say it. This will generalize the case I equals 2. So we will take 3 augmentations, and so we will keep 2 chords in my word. In my word, I will keep 2 chords and augment first by epsilon 1, then in the middle I augment by epsilon 2, and then at the end by epsilon 3. Okay.
Geometrized? Does it, take 3 and this is telling me that I can isotope this random filling to this one, but I cannot do it. I'm not allowed to pass to the third filling. What does it mean geometrically?
I mean, this is the M3 operation on the entire category.
Yeah. Geometrically, is it that? Is it,
Yes.
Wait. If they're different, when computing the massive product, that not being 0, does it mean that one of the random filling will isotopic, the other one maybe, if it's not isotopic, you don't take into account the third filling?
Oh, you could interpret it that way.
Yeah, talking about feelings, maybe one comment. I mean, these 2 and knots are very nice because somehow the feelings are classified. And in this case, all 5 augmentations are geometric, so you can actually see embedded feelings that correspond to them. And all of them can be obtained through, you remember that in the end of my talk I provided these operations, right? So whenever you really do resolutions with respect to all these crossings, right, in the middle, then you can actually write down all these five 5 filaments using this equator as a combination of elementary convergence.
So you're saying that the Legendre trapper with TB for 1 has 5 different
Yes.
Legendre
Yeah.
that are
And they are not
quite known
isotopic.
Hamiltonian isotopic.
They are known as Hamiltonians.
And then has results that generalize that to n.
They-
Okay. Are they smoothly isotopic?
They're actually Hamiltonian isotopic if you're allowed to move the Legendre. So
But if you fix the boundary.
There's a non-exact definition.
Okay.
Okay.
sorry.
Maybe I should have something that maybe a theorem from Bourgeois-Chantraine that the set of is as for the linearized Legendrian contact homology, the set of all bilinearized Legendrian contact homology for all the augmentation, for all pairs of augmentation epsilon 0, epsilon 1, all the isomorphism classes of bilinearized Legendrian contact homology for all pairs of augmentations is a Legendrian isotopy invariant. And so now I want to explain maybe how the bilinearized complex appears when you look at the linearized complex of the two copies. So I will explain. So I will write the two copy of lambda like this. So I have lambda 0 is the first copy, so it's lambda, and lambda 1, the second Legendrian, is a perturbation, a small perturbation of lambda plus epsilon dz. So you push off lambda 0 and then you perturb it with a small Morse function. And so if I take two augmentations, again epsilon 0, epsilon 1, you can obtain from this an augmentation of the two copy. So this is an augmentation of the two copy over Z2. How I think we saw this, how it is defined. You augment, pure chords are augmented by epsilon 0 and epsilon 1. Pure chords of epsilon 0 are augmented by epsilon 0. Pure chords of epsilon 1 augmented by pure chords of lambda 1 augmented by epsilon 1. And mixed chords are sent to 0. So mixed chords are not augmented. And so now I can look at the linearized complex of the two copies, linearized by this augmentation epsilon. So how it is decomposed? Well, the complex is there are three different types of ripcords. So you have pure ripcord. So, here you have, maybe I write C00 plus C11. So this is the vector space generated by chord from lambda 0 to lambda 0. Here from chords to lambda 1 to lambda 1. Then I have ripcords from lambda 1 to lambda 0. So this is those chords. And then I have some long chord from lambda 0 to lambda 1. And then I have some Morse chord. So I write CF so F is the Morse function I use to perturb the lambda 1. So those chords from lambda 0 to lambda 1 are, I call it long chord, and they go from the top to the bottom. From the bottom to the top. And my Morse chords, they are also chords from lambda 1 to lambda 0, but they are small chords. They are as small as I want if my perturbation is small. So I have all those chords, and in this big complex there are some subcomplexes. So C00 and C11 are subcomplexes. The differential on C00 is the linearized differential, linearized by epsilon 0. The differential here is the linearized differential by epsilon 1. And what else do I have? C10 is also a subcomplex with differential, the bilinearized differential. So this is a subcomplex because this augmentation does not augment mixed chords. So if I don't know if it's so is it clear that it's a subcomplex? And well, finally, this is also a subcomplex. So those are all red chords from lambda 0 to lambda 1. They are small one and long one. And this is a subcomplex with differential with this triangular differential. So there is a map, and there, this is the Morse differential. So you can ask why. Well, when I define bilinearized differential, first I defined it from the Chekhov differential, and I counted chords. I counted curves with boundary on my Legendrian, on R cross my Legendrian, and here I count. I say that I have this is the bilinearized differential, but I count chords on the two copy. But in fact, there is a bijection between curves with boundary on the two copy and curves with boundary on just on lambda. Okay, if the perturbation is small enough. So. Okay. So just before talking about augmentation category, so as for linearize, I write mu1 epsilon 1 epsilon 2 will be the dual of d epsilon 0 epsilon 1. And this leads to Legendrian contact cohomology of lambda. Really, I could say something about Lagrangian fillings, as we were. So, bilinearized Legendrian contact homology leads to a generalization of a Econ-Seidel isomorphism. So, if you have two Lagrangian fillings of a Legendrian, lambda, so sigma E for E equals 0 and 1. I have two Lagrangian fillings, so as Roman said, a Lagrangian filling, an exact Lagrangian filling, gives an augmentation. So I write, so this gives augmentation epsilon 0, epsilon 1. And so in fact we have that the Floer homology of sigma 0, sigma 1 is isomorphic to the Legendrian contact homology, the bilinearized one, bilinearized by epsilon 0, epsilon 1. And if you take epsilon 0 equals epsilon 1, so this gives you the linearized Legendrian contact homology, and this you obtain here the singular homology of the field. So this recovers the Eckhart-Seidel isomorphism. So maybe it's time to talk about augmentation category. Or maybe you have any question? No question. Okay, so this is just again a generalization of it. I don't want just 2 augmentations, but a lot of augmentations. So this is, the augmentation category will be an infinity category called Og minus of lambda. The object of this category are augmentation of lambda. And what are the morphisms? So the space of morphism from epsilon 0 to epsilon 1 is the complex of bilinearized Legendrian contact homology. D1, epsilon 1, epsilon 0. And in an infinity category, you have some infinity operations from of all order. So for all d greater or equal than 2, the case d equals 1 is the differential. You have an application epsilon 0 mu d epsilon d epsilon 0, which goes from epsilon d minus 1 epsilon d tensor epsilon 0 epsilon 1 to epsilon 0 epsilon d. So you have for each d plus 1 tuple of augmentation, you have an application mu d. And so what does it count? It counts holomorphic curves like this. Maybe it's not be clear. So if I have a chord in C lambda, so mu d epsilon 0 of chord. These are duals of chord, in fact. So maybe I don't write any formula, and I just draw what curves this count. So here we count A, and here you have B1, B, D, and here you have some chord, delta D, a world of chords, delta 1, a certain number of chords. And so you count those curves with boundary on R cross lambda.
What's going on with the deltas and the far ends?
What? Oh, here you have some chords, I don't know.
Just
So,
some extra chords.
Yeah, some extra chords, and then you use the augmentation to augment them. So,
Yeah, that's a delta 0 and not a delta 1.
That's
oh yeah. Okay, yeah, thanks.
So can I ask a question? In the generalization of the iconocytal isomorphism, is it infinitesimally wrapped? HF or fully wrapped?
I mean, the way I would think of it is infinitesimally wrapped is the same as the hum in the positive augmentation category. This one is like negatively wrapped.
Yeah. I don't know.
It's definitely not fully wrapped.
It's not fully wrapped.
I don't know. I don't know how it's called.
With the
With
shift
the other
boundary.
With a shift, yeah, that
Which
sounds
gives you
right.
which kills the illusion. Yeah, plus that. No. But then there's an extra thing that you can do, which is you can now take the end and move it back. That is usually the minimally plus.
I mean, what you really get here is through the isomorphism, you get relative cohomology, relative boundary, which by Poincare duality is the same as homology of the filling, but like properly, it's relative cohomology, and it's a, yeah.
Okay. Okay. Is it clear what those operation counts? Okay. So you count all those kind of curves and okay, and you augment all the extra chords.
like alternating between, like you do augmentation. Well, I guess the order doesn't
Yeah.
mean anything.
Those chords will be augmented by epsilon 0. Here you have some chords that you augment by epsilon 1, and those chords you augment then by epsilon d. Okay? And then so you do all these counts, the coefficient of the chord A in this will be epsilon 0, delta 0, epsilon 1, delta 1. Okay. So maybe it's not really clear. Right. As for bilinearized Legendre contact homology, you can see you can compute those operations in the k copy. In the k copy of lambda. So I don't know if I really want to do this because there are a lot of vector spaces. Well, the way to do is the same as for bilinearized. You take your k copy. So you have a lot of copies of lambda. Or k plus 1 copy, well, you perturb again to have a non-degenerate Legendrian link. And if you take augmentations of lambda, epsilon 0, epsilon k, then this will give you an augmentation of the k plus 1 copy again by sending mixed chord to 0. And then again, if you look at the linearized complex of k plus 1 with this augmentation, so this is a really bigger complex because you have a lot of chords, but you take this differential, and if you restrict to chord, so you restrict your differential to the subcomplexes of chords so of course from lambda E to lambda G, to lambda J, where where E is greater than J. So yeah, those are called from a copy here to a copy here. For example, called like this, from lambda K to lambda 0. And if you restrict your differential to those vector spaces, then you dualize, and the relation, the differential del square equals 0, you will recover the A infinity relations for the mu I. Okay. And in fact, in the K plus 1 copy, you can, if you remember what I wrote at the beginning, when you have A infinity operation, for each D, you have a relation to satisfy. And if you do all this stuff with the K copy, you can recover all the A infinity relations for all D smaller or equal to K. And then if you want the infinite relation for D greater, you take a bigger copy. Okay. Yeah.
Is there a uniform bound after which you know that things vanish?
You mean for D
yeah.
big enough
Yeah.
operation? Yeah. For Og minus, yes. For Og plus, it's wrong. But for Og minus, if you take a compact Legendrian, then you have a finite number of red chords, and then I don't know how to explain it.
It depends on your definition of uniform, though, right? So, I mean, if the differential
uniform for the
okay, maybe it's not uniform.
like about not uniform.
uniform,
Okay.
Just about.
for the Legendrian, I mean, the differential in the usual DGA, every word has some finite length.
Number of chords.
Now you can set it up so that with these dips, so that that length is actually 2, 3. Caitlin, what's the you dip, and then what's the longest length of the word in the differential? 3.
Okay, so in principle you can just look at the three push-ups.
The original and 3 push-ups, so it's 4 copies.
Oh yeah, it's K plus 1 to calculate mu K. You take K plus 1 copies. Okay. So. Maybe it can be useful to calculate the mu2 for some augmentation for the trefoil, or just I give you some non-trivial operation which appear in the trefoil. If you take so for the trefoil. At the beginning, we calculated the bilinearized differential for homology. We can calculate it for for cohomology. It's you just have to reverse thing. What you have is that mu1 of epsilon2 epsilon1 of b1. So it appears here and here. So you have a1 plus a2. And mu1 of epsilon2 epsilon1 of b3, it just appears here, so it's a1. And
It's like a grading shift.
what?
You have to shift the grading.
Yeah, but I don't. Okay, I don't talk about
Sure, yeah.
No, but it's okay. There is when you are in cohomology, add one. You add one to the degree. Oh, this will be a degree 1 map. The differential is a degree -1 map. And for example, one example of mu2. So I will maybe make an easy example. If you calculate with epsilon1, epsilon1, or epsilon2, epsilon1, epsilon1, of B3, B2. So there is, maybe it's a bit confusing because you have to reverse chord. So if you want to calculate mu2 of B3, B2, you look at you look in your differential where you have B2, B3, where B2, B3 appear. And for example, here you have B2, B3, and then okay, maybe it's not a good example because if I write B1, it will be if I write epsilon1, it will give the same result as if I write epsilon2. But so I write epsilon1, and then you can try with changing augmentation and calculate everything. So I look where I have B2, B3. I keep those scores, and then I augment all the others. And there I just have B1 to augment, and if I augment it by epsilon1, this gives me 1. So mu2 of B3, B2 is A1. And here I don't have B3, I don't have B2, B3, but B3, B2. So this is the only contribution for mu2. Okay, but so you can calculate everything on the threshold. Maybe I could say one thing which won't be really rigorous, but this category. So the main difference between OG- category and OG+ is that OG- is not a unital and infinity category, whereas OG+ is a unital category. So the point is that what plays the role of unity are the minima of Morse function we use to perturb the k-copy. So, if I have an infinity category, what is a unity first? The definition maybe is not so easy. So I have a unit. So this category is unital if for all epsilon 0 object of my category there exists a morphism E0 in epsilon 0 epsilon 0 such that mu1 of E0 equals 0 and mu2 of E0 A equals A, mu2 of A equals A. So this is for all A in epsilon 0 epsilon 1. So this condition have to be satisfied, and then higher product involving EI should vanish. So if I'm looking for unity for my category, I said to you that the minima will play the role of unity. So well, in the paper of École Metnayer and Sabloff. They rely curves with boundary on the two copy with curves with boundary just on lambda, and they give some bijection between set of curves in one side and set of curves on the other side. And if I look at right, so if I want to calculate some such products with here the minima of a Morse function, I have to look at holomorphic curves with A and a minimum M, which are negative asymptotics. So I want to look at such curves. I have a minima, and here I have A. So those curves will calculate mu2 of A and M, and I can have some other chords which are augmented. So this is if I look at curves with boundary on the two copy, so on R cross lambda 2 or lambda 3. But and if I they show that if I bring closer the different copies of my Legendrian, this will correspond to some strip with one mark point and a negative gradient flow line going to the minimum of the function f I used to perturb. And so here I have the A corresponds to a chord I write again A, but it's not really A. This is I have gamma, but well, in fact, what I obtain here is a neuromorphic strip in the symplectization. So this means that in fact A is gamma. So here I have the chord gamma. Or another way to say this is if I project in the Lagrangian projection, it will give those two chords project on the same point on the Lagrangian projection. So in fact, with this bijection on holomorphic curves with boundary on the 3 copy and curves on the boundary on with the boundary on R cross lambda, finally what I obtain is that here I have an A. So this means that when I calculate mu2 of MA, I obtain A. So this is a not rigorous way to, or maybe an intuitively way to understand why M is the minimum. And in my augmentation category in O minus, if you remember, if I take the K copy, I never consider small Morse chords, but I just consider chords from a copy at the top to a copy in the bottom. Okay, so that's why this category is not unitary. So maybe I can add just one thing. So if you remember talks on Monday, Roman told us that if you have an exact Lagrangian cobordism between two Legendrian submanifolds, this induces DGA morphisms on Legendrian contact homology. So, and in fact, this will induce a functor between augmentation categories. So if I have lambda plus lambda minus Legendrian, and a cobordism, an exact Lagrangian cobordism between them. We saw that this induces a DGA map from A lambda plus to A lambda minus. And also, if I have if epsilon minus is an augmentation of A lambda minus, then you can pull back this augmentation by this DGA map to obtain an augmentation of A lambda plus. So epsilon plus is epsilon minus composed with phi epsilon. And this is an augmentation of A lambda plus. Then using phi sigma, we can, well, I don't want to do all the, maybe I just draw what kind of curves the functor counts and that's all. So you can use augmentation to linearize this phi sigma. So you or even multilinearize it. Well, you do the same process as for the differential. You take the, several augmentation and you multilinearize those augmentation, and you can obtain from it a functor, an infinity functor from the category O minus of lambda 1 to O minus of lambda plus. So this goes in the other way. So an infinity functor, so F, this is a family of application, FD from D greater or equal than 0. With F0, this is the an application on object. So what it will be just the pullback by phi epsilon. The object here I augmentation epsilon minus, and then I want to obtain an augmentation of lambda plus. So this is epsilon minus composed with phi epsilon, and then I have all higher order operations. And what we count, for example, fd of epsilon d, epsilon 0 of bd b1, count what kind of holomorphic pairs, this kind of holomorphic pairs. So this is almost the same as before, but with the boundary is not the same. The boundary of curves is on the Lagrangian cobordism. So here you have some curves, some chords delta d, some curves delta 0, and other extra chords and b2, b3, etc. But those holomorphic curves are with boundary on sigma.
I have two questions just to remind.
Yeah.
First of all, phi epsilon is actually phi sigma, right?
Oh yeah.
It's
Okay.
phi sigma.
Yeah.
Second of all, can you remind me? I just want to figure out where the contravariance is coming from. Is the induced map on Legendre contact homology already from plus to minus? Or is it because this is sort of...
Oh yeah, yeah. Well, yes.
Okay,
Yeah,
so
yeah.
this is just the same.
Yeah, yeah.
Okay.
Yes, in fact, well, I don't want to write the infinity functor relation, well, but I can just say that, so there are relations that are satisfied, and the first relation for d equals 1, the first relation is that f1 composed with mu1 equals mu1 composed with f1. So F1 is the DGA map. So this corresponds to the map induced on Legendrian contact cohomology.
Okay. Yeah.
Because I have not the differential, but the mu1, which is the differential of the cohomology. And for d equals 2, I have, what do I have? I have F1 composed with mu2 equals mu2 of F1 plus extra terms involving mu1. So that means that in homology, F1 preserves the product. So the product in my categories. And then for d greater, I don't know what it means, so but just this means for d equals 1 and d equals 2. And maybe just to finish, it won't have a lot of sense, but even if the augmentation category, even if aug minus is not unital, there is you can so you cannot say that you cannot define, well, you have not a quasi isomorphism relation between them because they are not unital, but you still have a pseudo equivalence relation that I don't really want to define. But the fact is that if you have two Legendrian which are Legendrian isotopic, this implies that the augmentation categories are pseudo-equivalent. Well, there is an infinity functor between the two augmentation categories, which is a pseudo-equivalence. And there is a definition for pseudo-equivalence, which is it has to be a cohomological full and faithful functor, such that each object is isomorphic to each object. Epsilon prim in one side is isomorphic, pseudo-isomorphic to an object f epsilon. But the problem is to define the pseudo-isomorphism, because as the categories are not unital, you have to, well, there's a way to define an equivalence relation between augmentations, but this uses adjunction, well, some difficult algebraic things. Okay, so I had I think I will stop here.
Sometimes, if I remember correctly, there's some trick to add in by hand a unit.
To what?
When you don't have a unit, there's a trick to add in one by hand.
Yeah, you made it a million.
Right. So if you did that, would you have, I guess, would you be able to say that things are equivalent? Categories are equivalent?
I think that's more or less what pseudo-equivalent means.
Ah, okay.
If I remember correctly. Maybe somebody who knows more homological algebra.
I don't know.
What kind of invariants can you squeeze out? I mean, how can you effectively tell where the two augmentation categories are not semi-equivalent?
For example, if you don't have the same number of isomorphism classes of augmentation, Well, maybe I should have mentioned, well, I said at the end there is a way to define an equivalence relation between augmentations, even if the category is not unital, you have a way to define an augmentation relation. And so this is also a theorem that if epsilon prime are equivalent, then it implies that, so maybe epsilon 1, epsilon 2, it implies that for all augmentation, you have that epsilon 1, epsilon of lambda should be isomorphic to LCH epsilon 2 epsilon, and you have also an isomorphism when you invert, when you say epsilon 1 and epsilon 2, and so okay, this doesn't really answer to your question, but if you don't have the same, what I wanted to say is this can be used to show that the 5 augmentations of the trefoil are not equivalent.
But it's useful to say that if you really consider augmentations inclusive too, then you have only finite number of them. So really like number of objects in the category.
Yeah,
isn't
sure, but that's about
if you consider if you consider something in the bigger ring, let's say Z or whatever, then of course it's a different story.
But it's a very coarse invariant, right?
What's it?
It's a very coarse invariant.
Yes,
like if you get
from
manifolds like
if you really consider number of
characteristics.
That's true. That's true.
But for instance, you can use M2 on the homology of this category, so just the product operation. So you have some sort of ring-like thing on here, and you can use this to distinguish between different Legendre knots.
So you have some
or even
algebraic nonsense that you
higher,
can apply even if it's on.
yeah, or higher products as well. So that paper with
Yeah.
the many authors.
Yeah, with
that you
the
mentioned.
first paper, well, with all the authors, Sivan, Kuprowski, Etnayer, Walker, and Sabloff, where they define the A-infinity algebra. So they use the product structure to distinguish some Legendrian. Yeah.
Can you just say a little bit more on this? Why do you need a unit to define quasi-isomorphism?
Well, I never remember how to define the. I'm sorry, I never remember the thing. If you want two objects to be isomorphic, oh yes. So epsilon 1, epsilon 2. So if you are in a unital category, you say they are isomorphic. If there exists and maybe B also on, so that the composition will give so that when you compose the A and B, you obtain E2. Well, exactly the kind of unit you don't have in Og minus.
Right, but this is for two objects in a category to be isomorphic.
Yeah.
Like where there exists a functor from one category to the other, like full paper or something, an isomorphism of homology.
So
where is the
So, to define equivalence of categories, you mean? Do you want to define equivalence of augmentation or equivalence of categories? To define the equivalence relation between.
You need that relation. Okay. Yeah. Okay, thank you. Yeah, I understand.
Keeps the equivalence classes between
the
equivalence classes.
So full and faithful is not a well-defined thing. You don't have units.
Full and faithful, what?
It's hard to make sense of what it means for a functor to be full and faithful if you don't have an identity.
Okay.
I guess this is what it was. It's hard to make sense of a functor being full. How do you define two things? You don't know how to define two things are isomorphic in the target. You don't have isomorphism
Yeah, yeah,
classes.
yeah.
Or it's hard to define isomorphism class. What? Yeah, but you need to hit all isomorphism classes. If
Yeah,
they're not
full is
well
something
defined.
like everything in the target is isomorphic to
Yeah.
something in the image,
Yeah,
and
yeah.
then if you
So
don't
yeah,
have
yeah, that's what.
isomorphism, then
Yeah, yeah, that's what I said. Yeah, in the pseudo equivalence category, you need the equivalence between augmentations. That's why they defined a pseudo equivalence relation between augmentations, even if the category is not unital. To have a pseudo equivalence relation between categories. Yes, yes.
Do you know why don't you just work with the unital version? What is it, Aug Plus? Is that the one which includes the Morse?
Oh yeah.
Which
Oh,
is
oh well, yeah, yeah. In the K copy, I said you can recover the aug minus operations using chords going from lambda 1 to lambda 0 or lambda k to lambda 0, etc.
Yeah.
In fact, to define aug plus in the K copy, you look at the vector space generated by chords going from 0 to 1, but then you don't have a bijection between chords going from a copy to another with chord of the Legendrian. You have the bijection if you consider chords from lambda 1 to lambda 0, etc. And if you look at chords going on the other way, you have also Morse chord, and that's what you consider an aug plus. And so intuitively, that's why this category of plus will be unital.
But it doesn't have the net relation with your original. It doesn't have that bijection with your original set of chords, so that's why.
Yeah,
it's not as nice.
yeah, there are more chords.
Maybe I can add that. Yeah, so maybe this is historically why aug minus was come up with this, because it depends only on the DGA of lambda itself. Whereas, well, aug plus sort of, that is also true, but maybe not in general if you use higher dimensional Legendrians.
Is the information contained in the two categories different?
Quite different. So it's aug plus is like you take infinitesimal category. Aug minus is that if you are joining units, it's like compact category of the Weinstein manifold with handle attached. So originally aug plus, you don't attach any handle, you attach like quaternion cones.
Yeah, I would say they do have.
Minus is like wrapped under attachment.
Minus is that, so it's non-unital, so if you attach handles and by capping off the Lagrangian disks which are filling, then you get units. So that's the compact category, basically. But there is problem of generation, but in general it's not true because Lagrangian spheres, they don't generate category in many cases.
But finally, yeah, aug plus, you can recover it from this enhanced DGA that back home luckily with the loop space chains in the loop space.
Alright, do we have more questions? If not, we're reunion at 3:45.